In one of our earlier videos, we had seen this equation x beta is approximately equal to y, where this system could be inconsistent. Now we wanted to solve it in the least square sense. For this, we had given a strange magical prescription. Pre-multiply both sides by x prime and then just ignore this approximate inequality and treat it as exact inequality. Now this resulting system of equation we called the normal equation, and we suggested that we have to just solve this for beta and then we shall get a least square estimate of beta. Now this magical approach naturally raises two questions. One, why should this magic work? And two, can we always solve the normal equations? Will this system be consistent? We know that the original system may be inconsistent, but we just pre-multiplied both sides by the same quantity and we are saying that this system must be consistent. Where is the guarantee for that? So let's answer these questions one by one. We start with the first question. When we were trying to solve this approximate system in the least square sense, we had this picture. This is column space of x, and our plan was to drop a perpendicular from y onto column space of x and take this vector. So this is the closest that you can get of this form x beta, closest to our given vector y. Now when I do this, what I am doing is this. I am taking this particular vector, which is y minus x beta, and I want this vector to be perpendicular, orthogonal to column space of x, which means I want this to be perpendicular to every column of x. Now suppose that the columns of x are x1 to xp. So when I say that this vector is orthogonal to x1 in terms of Euclidean inner product, I actually mean x1 transpose times this vector is equal to 0. That is the definition of Euclidean inner product. Similarly, when I want to say that it is orthogonal to x2 also, I mean this. In general, this must hold for all I from 1 to p. So if I bunch all these things together, in that case I can write x transpose. And that is exactly how I got the normal equation. So this is why the normal equations are going to work. Now for the second question, why should this system of equation be always consistent? Well, here this is the coefficient matrix and this is the vector of constants. So we know that this will be consistent if and only if this belongs to the column space of this. Now I said that this is going to be consistent whatever x and y you take, which means whatever y you take, x transpose y must belong to column space of x transpose x. Now every vector of this form x transpose y, whatever y you take, that constitutes precisely the column space of x transpose. So if we can show that column space of x transpose is a subset of column space of x transpose x, then we are done. Now we already know the reverse inequality. So we know that this always belongs to column space of x transpose because it is obtained as x transpose times a matrix. But we need the reverse inequality. However, there is a result from linear algebra which says that for real matrices we have rank of x transpose x equal to rank of x transpose, which means that the dimension here is same as the dimension here. Now here is a subspace and also its dimension equals the dimension of the entire space. This naturally forces this inequality to be equality. So they are saying, in particular you might even say that this is contained in that. In fact, they are the same. And that is why we know that this system is always going to be consistent.